This is a demonstration of a parallel city block implementation in the processing language. What we're looking at is a 20 by 20 by 20 grid of data, and white cells are healthy, non-featured cells, and the cells that are green and red and that other kind of grayish color in the center you see here, those are the feature cells that we've created randomly, and we create basically spherical shapes. However, as you can see, they can grow together and clump. To really see what's interesting about the parallel part of this, though, is we need to look at the output from the program. So if we go over to the screen where we've run it, you can see here that we started off on the vertical side. We'll just look at that, looking at depth 0 to 2 for the 20 by 20 slice, and they both ran just like 2 and 3. But then suddenly we jumped to 18 and 20, and we only run 18. And then we look at 4 to 6, we managed to run 4. Then we catch up to 19. Then the program does 16 to 18, where only 16 runs. Then 14 to 16, and basically, there's no real pattern to how this is behaving. It's simply performing the different slice computations when the processor is scheduled to do so. And as a result, as these data sets get really large, which is not something that we can feasibly demo on this particular system, when those data sets get really large, you'll see immense improvements over a serial implementation by about 50% of execution time. So coming back to this image, just to look at it a little bit more, we'll remove a couple features that may be hard to look at just because of how large this image is relative to the screen size that we have. But we clearly took a chunk out of there. We remove another feature, it disappeared over on this other side. And you can see here this green color. These are all cells that have been manually set to 1 because they neighbor a cell that has been removed. And we don't want these cells, even if they have a path to a healthy cell, they're not strictly orphaned in the sense that it's floating all by itself surrounded by removed cells. Even if it has a way back to a healthy cell, we can't allow it to have a value greater than 1, because if we did, the removal algorithm, if one of these was, say, a 2, then it's going to step into a removed area and re-remove that cell. And when we're looking at this as kind of a cancer treatment, we certainly wouldn't want to be re-removing cells from a patient over and over. That would cause probably more trouble than it would solve. So we'll go ahead and just finish removing all the features. And each time it does this, it finds the next biggest cell and removes it, and then recomputes all the distances. So that's why it takes it just a second or two there to complete, because it really is doing a lot of work. And now you can see we've got this really kind of interesting shell left over, and we can add our spheres in. This will really kind of hurt the processing. It'll slow it down a little bit to have all this, but you can see they kind of tend to intersect and clip a little bit. Merely a limitation of the city block transformation, or the city block algorithm, because of how it's so linearly stepwise. But nonetheless, the cells that it covers are still there. They're still considered to be healthy, and there is parallel implementation.